Hi guys, welcome to Learning Electronics Repair and the ongoing saga of the Class D amplifier. But I've learned quite a bit during this repair and I hope some of you guys have as well. There's been several videos on this. The fault is that the bass, the subwoofer, is very low volume, but the satellite speakers, the tops, actually work. And we know from previous videos, and I'll link them here, that we have 4 amplifiers on here. Each one has a pair of MOSFETs, that one, and this one. Okay, 1, 2, 3, 4. Each one is a Class D amplifier. We know we have 4 signals coming in, which are basically all the same amplitude as each other. We've measured that. And the signal comes from a little daughter board. You can't see, it's under here. We can look if we need to. And it comes down onto these chips here. So this one, there and there. That is pin 1 on these ICs. These are the MOSFET drivers, and then effectively they drive the gates of the MOSFET. So this will have a pulse width modulation on it, going between 0 and whatever volts. I didn't really measure. It might be 15. That was the positive supply into the op amps and stuff. It might be something else. We will find out in a moment. So every time that goes high, it turns on the high side MOSFET, and every time it goes low, it turns on the low side MOSFET. So this chip effectively is switching these alternately depending on if that pin 1 is high or low. Now, on the previous video, we realised, or I realised, that on the Class D amplifier, even with no audio input, all of these output transistors or MOSFETs are still running, and they're running at 50% duty cycle. So what we should see now with no audio input is on each of these pin 1s, we should see a 50% duty cycle signal. And we should be able to see that on the gate of each of the transistors as well. So this is what we're going to do today. I have my little handheld scope. It's isolated, but I've connected the ground to the negative supply rail. We also figured out this is actually a single supply rail on here. So it's a plus 150 volt supply. It has 0 plus 150. And then it has a return for the speakers, which is connected to a junction of some large electrolytic capacitors, basically. A bit like an ATX power supply works, okay? But we're not going to worry about that side of it. I explained all that in the previous video. What we're going to do now is power this up and have a look to see if all our 4 amplifier channels with no signal, no input, have actually got this 50% duty cycle square wave, okay? I'll just zoom the camera out a little bit. You can see everything on the bench here. So these are the LEDs. You'll see there's no inputs connected at the moment. We have the power LED and we have the signal LEDs. So these should all come on. These should go red for a few seconds and then turn to green as the circuit protect comes off. So let's switch this on and let's have a look and let's see what it actually does. Well, they all come on, red, and they go out. Okay, so protector's off. So what I want to do now is have a look to see if I have the drive to each of the MOSFET drivers from the 4 channels. So one of them is here. And I'll just hit auto on my scope or moment, but I can see there's a square wave on there. Just change the frequency down a little bit there. Let's see if I can trigger that. But I can see straight away it is a 50% duty cycle. If I just get the trigger set. It's set to trigger on channel 2. I'm actually on channel 1. Okay, I've triggered it. I've put it onto hold. You can see that is 50%. Okay. Go back to run again. Let's go to the next one. So we're going to the next one, which is actually here. Okay, what do we have? Auto again. Well, this one seems to have a problem, okay? That one appears to have a problem. What's on the next one? That one is running. Okay, I have it. I'm not very familiar with using this scope. I have so many of them. But again, that's 50%. Okay. And the 4th one is here. And that's also running at 50%. So 3 of them are running at 50% and channel 2 isn't running. Okay, so the problem is that we have no output on this pulse width modulator into the MOSFET's driver on this channel. And I suspect this is the one that isn't working. So what we need to do now is to trace to see where that signal's coming from. I know it's coming from one of the LM319s, but we can trace through to which one. And then have a look at what's happening on the LM319 on the inputs. Is the LM319 faulty, or is there something wrong with the input? And we'll try to work our way back now. We should be able to find out why that channel doesn't run. Before I do that, I'll just make sure this is safe to work on. So I'm just going to check across the large capacitors to make sure they have discharged. Okay, I have the multimeter on volts. Let's have a look. Yeah, they're down to about 1.7 volts. So 1.3. I can safely work on it. And the second one in from the end, the one that wasn't running, this one, we can see that goes up here to a pin on here. Okay. And that comes through, because I traced this through before in the previous video, to one of these chips on here. Okay. And I think it was on pin 12. Yeah. Pin 12 of that one. So that's the one that seems to have some sort of problem. So I've just scratched a mark onto it so we remember which one it is. These are the LM319. Pin 12 is the output, which doesn't have any output, or at least no pulse width modulation. So let's have a look at the data sheet and see which the relevant inputs are on here, and then take it from there. So pin 12 is the output, and the inputs are pins 5 and 4. Okay, so we could have a look at pins 5 and 4 on one of the good channels and on this one, and let's see if we can see any difference with the input, or maybe this chip is just faulty and the output isn't working. But I'm sure by comparing one of the good ones with this one, we should be able to make some sort of sensible diagnosis from that. Because it can be quite difficult to probe around these chips without slipping, I'm just figuring out if I can find better points to set the probe. So that's pin 5. This is one of the good channels, okay? And that clearly goes to there. It also goes to here, and it goes to here. And then we can look on this. This is the bad channel, and much the same. We can see it goes here. You can hear it, yeah? And it goes here, so you can hear that. So we can probe pin 5 on here, and then pin 4 doesn't seem to go to anywhere, but I'm sure it will. Yeah, it goes to there. This one? Yeah, it goes to there as well. You can hear that as well, yeah? So we know we have a connection from here to pin 4. We have a connection from here to pin 5. And then the same on this one. One would assume. Pin 4. Pin 5. So we have easy points to probe. I've had to turn this around so I can still plug the power in. It comes from here basically down this cable, which I need to attach. So I could solder some wires and stop having to do that, but out of interest, that's where it does come from. I'm a bit interested to see what DC voltage levels I have here, as well as what the scope tells me. So let's just check that. Okay, it's a bit hard to get down under this lot. I may be able to disconnect these as I have no signal, but I'll leave them on anyway. We can look at the first ones because we know this one's good and this one's good. This one is bad. Okay, so for this one, we have 10.7, okay, and this is 10.7, so they're both 10.7. Next one, 10.7, 10.7. So they're basically balanced. Yeah, this bad one is 2.2 and 10.6. So there seems to be something wrong down this one. Now we can compare that with one of the other good ones. So this one here, 10.7, 42. So there's quite a voltage drop across that. 2.2. There's no voltage drop across this one, but there's quite a voltage drop across that one. Okay, then that comes from this one down here, which is 43. I'm guessing this is reading 2.2. Yeah, and then the other side of that, this is 151. Okay, and then just get one of these other ones I can actually get to without shorting anything out. That one, 70. Okay, so there's a very large voltage drop across that one, and less against that one. Let's just get a thermal camera. Let's see if that tells us anything. Zoom out a bit so we can see. So here is our PCB. Something is quite warm down here. 43, 44, 42. So these are the two good ones. 42, 42. Then the next one is the bad one. Okay. Then the last one's a bit harder to see. Okay, there. Let's switch this on again. So what do we have? Well, 46, 47, 46, 46. So they're all about the same temperature. These resistors are about 60. Where's the one that's actually 60? And then the channel that isn't working, the resistors are cold. Okay, the resistors are cold on the one that isn't working. Okay, I've just poked around a little bit. So this is the one where we have the 150 volts on the end of it, and this is reading 2 volts on both ends. Okay, and that goes down to the second chip in the bad channel, and it goes to there. Okay, and if you look at the next one along, which is one of the good ones here, that I think goes to the same pin on this one. Yeah, so this goes through to this pin. Now this is pin 1, 2, 3, 4, 5, pin 6, and you can see that is the junction between the drain of one of the MOSFETs and the source of the other one. Okay, on this channel, same thing from here. Goes to there and there. Now, these MOSFETs, we know, are connected effectively across the positive and negative supply, which will go from here. Will be one of them. That'll be the drain of this one, I think. No, drain of that one goes to there, and then the big heatsink, which is the negative supply rail, goes here. Okay, so we have basically the source of this one going to the drain of that one. Okay, this being the source and this being the drain. So this point is actually like the junction, and this should be 75 volts. It's half voltage. If they're running at 50% duty cycle, that should be 75%. Now on this one it's not, but we know this isn't running at half duty cycle. So we've got a situation here where either we've got faulty MOSFET, or one has just been switched on and one is off because this driver isn't running right, and then that feeds back into the op amp, and then we can't see if the op amp is running right because it's a kind of a loop. Yeah, it's kind of a loop, and that won't really tell me whether the fault is this or the driver or the MOSFETs, to be quite honest, on that channel. And I think the only way to find out, well, we could take this board off, but it's not particularly easy. And we could see if we can see any other differences around here, but I'm not sure we will. So I have a situation at the moment where I know I have a fault on this channel, but it's almost impossible for me to say whether the fault is because of some input condition on here, or whether it's a fault caused by some problem with the driver and the output on the same channel. Yeah, that's interesting. Although we don't have a schematic for this, I can see a few more things as well. So I can see from the junction of these two resistors, and the same for all of them, we have a connection there which goes somewhere. Okay, so we know there's a connection from there. We may need to reverse engineer and trace that. I can also see from here, so this is pin 5 going to the end here. There's a resistor here, and that goes off in that direction. Again, we can see a similar thing on this one that goes to a via. This one, it goes to a transistor, or actually it goes to a via and a transistor. So that one definitely goes to 2 places. These may well go to 2 other places. This resistor is marked 01C. That's an SMD code. It's one that I do know. It's a 10K resistor. We can just check it. How's it read in circuit? Yeah, it reads 10K. So we know we have a 10K resistor from there. And then we have another component here. This looks like a capacitor. And the other end of that, probably, yep, ground. So we know we have a capacitor from this end to ground as well. But I believe we actually now have all the information we need to diagnose exactly what the fault is on this. We have all the clues, so let's put the clues together and let's work out, just based on what we know, what is wrong with this. So we'll start again with the data sheet for the LM319. We can see pin 5 is the inverting input and pin 4 is the non-inverting input. And on the good channels, both of these have about 10.6 volts or thereabouts on them. On the bad one, this has about 2 volts or just thereabouts, and this is about 10. And the output on this will depend on the voltage and or signals on the inputs. And we know that these LM319 drive the IR2184. We have a data sheet again. We have in, and this has a square wave 50% duty cycle on the 3 good channels. So from that, we know that one of these inputs at least has a square wave on it. And it's comparing that with the other one. Effectively, it's a comparator, we know that. So one of these inputs will have the square wave on. This pulse width modulation output, we know. Otherwise, we wouldn't have a square wave on here. And we wouldn't have a square wave on there. That then drives this chip, and this switches the 2 MOSFETs on and off alternately. Ours is wired a bit different from this, in as much as our 2 are connected together in series, and then we have a single output going to the speaker, okay? But it's the same sort of thing, so these are being switched in series. So we know that as well. And we also know that those 30k resistors in series are monitoring the voltage here and all the square wave signal, and they're feeding that via the 2 resistors, and there's a few other things connected here back into here. Okay, so that's what we know we've got. We can draw this out. We've got some voltage readings, and I'm sure from that we can work out exactly what the problem is. So, a slightly grubby bit of paper. I need to buy a new book. This one is just about done. Okay. But this is basically what we've got here. We have the comparator. Inverting, non-inverting inputs. Okay. From the comparator, we know that drives the MOSFET driver chip on pin 1, which is in. Okay, so this is the IR2184. This is, of course, the LM319. Or half of it. There's 2 of those in that package. Okay. Pin 5. Pin 4. This is pin 7. And that, we know, goes to here on pin 1, which is in. Okay. And this is driving the 2 MOSFETs. So we have 150 volts. We have the first MOSFET, the high side MOSFET. Then we have the low side MOSFET. And then we have chassis ground, 0 volts. Okay. And this chip drives these 2 MOSFETs, like so. And if we have a quick look on the data sheet, and we'll get rid of the multimeter because we don't need it at the moment, okay? The data sheet, well, we'll see that this point, which is the junction of our 2 MOSFETs, also goes to this chip, and we know it does because we've tracked this out. This is pin 6 on the chip, this pin VS. High side floating supply offset voltage, that's what it's called, and that is pin 6. So we know there's a connection here to here, VS pin 6. Okay. We've seen that the MOSFETs are wired like this in series, we know that. Then we have from here two 30k resistors. Okay, that then goes to pin 5. So this is 30k. This is 30k. Okay. We know this goes to somewhere. We don't know where it goes to somewhere. And we also know that from here, we have a 10k resistor, which also goes to somewhere, possibly 2 places. Look at another channel. And we have from here, a capacitor to ground. Okay. So we know we have that. On a good channel, let's have, what did we have? On here, pin 5, we had 10.72 volts, okay? And on pin 4, which obviously goes somewhere, I had 10.74 volts. So they're very similar, okay? On the junction of the 2 resistors, so here, I had 42.9 or 43 volts, depending on which one I measured, okay? And on here, I had 75 volts. Now that's the junction between the 2, and that's half the supply voltage. And that's because we know these are switching on the 50% duty cycle. So that's what you should have. What about our bad one? Well, on the bad one, here we had 2.215 volts. Okay, that's bad. I'll put a asterisk by them so we know which are the bad ones. That's a bad one, okay? On here, we had, what was it, 10.62 volts. Okay, so that's another on the bad one, okay? On the junction between the two resistors, we had 2.251 volts. Okay, that's bad. And then on this end of the resistor here, we had 151 volts. So that's the bad readings that we have. Okay. What does this tell us? Well, it tells us a few things. First of all, it tells us that on the good channel, we have, subtracting that from that, I've already done it, it works out at 28.1 volts. So across our resistor is 28.1 volts. Okay, and from that, with Ohm's law, we could work out the current that's flowing through that resistor. Okay, but we probably don't need to. This resistor, across from there to there, has, again, that subtracted from that is 32.18 volts. Slightly more. So we can say with certainty this resistor is passing a bit more current than that one, because the resistance value is the same, but we have a slightly higher voltage drop. So it's passing a little bit more current. Now, the input of an op-amp doesn't draw any current. That's the whole point of an op-amp. So either some of the current is flowing that way, but that still doesn't explain where the current's coming from, because you can't have more current going through there than is coming in through here unless there's some more current coming in from another direction, which must be there. Okay, so we know that. On a bad channel, we have a much higher voltage across here. And again, we can work it out. So 151 minus the 2.251 actually comes out at 148. What is it on my calculator? 75. Okay, close enough to 2 digits. On this resistor, on the bad one, we have a little bit of voltage drop here as well. We have 2.251 minus 2.215. So there's a little bit of current flowing this way. Nowhere near as much because the voltage drop is much less. Yeah, it's, what is it? 0.046 of a volt off the top of my head, something like that. Okay. So that's what the voltages tell us. Now, there's two other things that we can learn from this. One is that the output of this op-amp is dependent on the voltage on the two inputs. And in our fault condition with only 2.2 volts on here, that is a lot less than the 10.62 on the non-inverting input. So the output of this op-amp will go up to the rail, it'll go high, up to its supply voltage, probably 15 volts, I haven't measured it. And that will put a high on pin 1 here, and in turn that will turn on the high side MOSFET. HO, high out, low out. So the fact this MOSFET is switched on means the 150 volts is on here, okay? So it's kind of like you might think we've got a chicken and the egg situation. It makes sense that the output is high. It makes sense this is switched on because this is on, but this is on because of the high voltage on there. Do you see? We have a loop. So what's the real problem? Well, the real problem, we could work this two ways. Why would the voltage here be 2.5? Think about it. Why would the voltage here be 2.25 rather than 42? Ignoring the fact that side's higher as well, even more so. Why is the voltage here so low? Well, there's only two reasons for that. One is from here, we have effectively a near short to ground. Something is holding the voltage down. Something like a transistor that's gone short or something like that. I mean, we don't know exactly what this connects to, but that's one reason. The other reason why we'd have a very low voltage here is that because this resistor has gone high, the resistance has gone very high, so the voltage drop across it would be much larger, higher resistance. Yeah, we could measure this because we could actually check from here for a near short to ground, but we have one more clue. What did the thermal camera tell us? It told us on the bad channel that these resistors are cold. On all the good channels, they're about 45 degrees. They're passing some current. If we had a short here to ground, this one would be glowing like a Christmas light, probably. Or it might just burn out, and then in which case it would be cold. But this would be passing a lot of current if there's a short here, assuming this hasn't failed. Okay, so the other likelihood is that this resistor is high. It's not open, it's passing something, unless there's something's coming down here, it could be open. But the problem is either this resistor or a short on the end of it. So let's measure that resistor. Okay, so, well, here's a good one. We'll go to this end, it's the same end. They're all the same value, 30k. Yeah. 30k. Let's look at ours. 30k. Ah. 4.4 mega ohms. That's close to being open. So that resistor has failed. It's very high resistance. Hence the fact we've got a very low voltage on here and the whole thing doesn't work. Why did the resistor fail? Two reasons. One, it's under stress because normally this has quite a high voltage across it. It's passing some current. We've seen the 45 degrees, these things. That's one reason. And to be quite honest, when the amplifier is driving, the voltage on this end won't be 75 all the time. It'll be going down towards 0 and up towards 150. So these are doing some work. So one reason it's just failed. It's just tired. It's given up. The other reason, like I said, is that we have a short or a low resistance from here to ground, and that's caused the resistor to fail. Well, we have 4.8 meg, so we don't have a low resistance to ground. It looks like this is failed just by fatigue. Is that a good way to put it? Fatigue. So I think the next thing that's sensible to do is to change that. And I just can't do it with this board attached. I mean, I just don't, well, I mean, this is right by it. All this plastic's right by it. I think, in fairness, I'm going to have to take this whole board off just to change that. I mean, that's a pain in the butt. You know, maybe it's too much of a pain in the butt and we'll try to do it with a soldering iron. Let's try to change that resistor. Sorry about the lack of focus. Let's try and change that resistor without having to take this whole board off. Because, honestly, guys, I can do it, but, you know, if you don't have to, you really don't want to do. Yeah, it's got all these pins here, and then it's got 2 rows of them there as well. Okay, let's see what we can do. Well, we can't use hot air, for sure, because of all this stuff. I hope you guys don't think I laboured that point a bit too much, the diagnosis. I mean, I know you guys have a lot of different abilities and skill levels and knowledge, yeah. Some of you know more than I know, for certain. And especially in certain areas. I know some of you guys are experts on these type of amplifiers, and you rightly call me up on the case and say, Rich, you want to rethink that. Yeah, we're all learning. But I felt I needed to do it that way because that sort of fault diagnosis is important. We can all take readings. Yeah, we can all see what's connected to what. We can all read the data sheet. The thing there was to figure out what must be the problem. We came down to 2 possibilities, and the evidence said that one was much more likely than the other, and then we found it. But let me know, guys. Comments, tell me what you think, yeah? Okay, guys, this is not going to be easy, and I'll guarantee you on video it's 3 times harder, at least. Yeah, that's just like sod's law. It's not easy to get this under the microscope, especially the optical one, because this is like sitting so far from the bench. Yeah, it's so high. So let's see if we can do this without making the right pig's ear of it. Worst case scenario, I'm going to have to take this board off, yeah, but I'd rather not if I can avoid that. Yeah, so first thing, come in here with some leaded solder. Okay, I'll try and get some on the other end as well. I've got it, and hopefully I can get this off by heating from one end only. Hopefully. There you go. Just clean that one up a little bit. Right, so we have the thing off. I think this is just flux that's on here. I honestly don't think I've melted that chip. One hopes not. Nope. Now I have to find a resistor, so the question is, do I have the right wattage? With SMD resistors, that basically comes down to the right size. Well, as Sod's Law would have it, I don't actually have 1206 resistors. Neither does Detlef. I have 2512 and then 0805 and all the smaller sizes down to 0201, but for some reason I never got 1206. A quick look on AliExpress tells me I can buy a full pack, 25 each and 80 values, including the ones that I want, or just one I want, 30k, for €4.60, less the 21% VAT and free shipping on orders over €10. I've put it in the basket. I have €26 worth now, so I'll order those, at least I'll have them in future. And I've asked the guy who brings me these from IFPUDEUV, the company who brings me these things, over the other side of Gran Canaria. He's near to the capital, so he's going to go into the local electronics shop and ask if they have one. Not only do we now know what's wrong with this, just looking at this circuit, this effectively is forming a kind of negative feedback. So to set the gain of an amplifier, you normally monitor the output here, yeah, and feed that signal via a resistor back into the input of the amplifier basically, and that sets the gain of the amplifier. And this is doing a very similar thing. So we have effectively a couple of resistors, then this capacitor. So although this is pulsing here at high frequency, what you will get here is almost certainly the audio signal without the high frequency switching noise, can we call it, in there. Okay, and it's comparing that with this. This may not be a square wave coming in. This could well be a sawtooth wave coming in here, or a triangle wave on there. So at any given point, it's comparing the level of the audio with the sawtooth or triangle, and that effectively will generate the pulse width modulation that will modulate the width. So I can sort of see, I mean, I'm not an expert, but I can definitely see this as a form of negative feedback, and it reminds me very much of what I would see in a class AB amplifier. So again, guys, you know, talk about it in the comments. And given the fact we have an open circuit resistor here, basically it's like having a very high value feedback resistor. This is probably forming a voltage divider of some sort to set the level here. So a high value resistor here, which was near on open circuit, 4 meg, effectively would make the gain of this circuit very high, which also really explains just why this is getting up to the maximum voltage, you know, switching that on and sitting there, because the circuit's doing what it should do as a feedback loop, but that just completely upsets it. I've spoke to the owner of this one. He went to the local electronics shop, Lopacan, and they don't have any 1206 surface mount resistors either. In fact, 30k they only had through-hole ones. So he did bring me some 30k through-hole ones. They're not particularly accurate, and the resistors on here read very accurately. So I said, well, you can't use these, but he's persuaded me for now to fit just a through-hole resistor. So what I've done is I've gone through my stash of 10k resistors. I looked at 15k, but they all read lower than they should. I didn't have many, But I had a lot of 10k resistors, and some read high, some read low. So what I've done with these, I've selected 3 of them, connected them in series, you can see here. And these are reading 30.04, 0.02 even. That's as good as the surface mount ones that are on there. Now, before somebody says, and you'll be right, possibly the temperature coefficient is different for these type of resistors than the surface mount ones. Maybe the value will change in comparison to the other ones. And this is part of the feedback network for the whole amplifier, basically. It may not work, or it may not be completely stable. Now, I have told the guy this, that there's no guarantee, even if this works, which it probably will work, whether this will actually work properly over long periods of time. But he says, well, you know, we have to wait for the proper ones. I've ordered some now anyway. Get it done. So, you know, instructions from the owner, it's going to happen. So I'm going to put a bit of heat shrink over here. I have no concern over the wattage. I think these are a 1/4 watt or 1/2 watt each, but I've got 3 in series, so that will be divided. They're all equal value. I can solder that on there easily enough. There's plenty of space in here. So this is going to go on, and then let's see if the amplifier actually works. It shouldn't be difficult to solder this on here. In fact, easier than soldering another surface mount, most likely. I don't want the resistors to short together, the legs, so I'm going to put a bit of heat shrink on here first, and then cover it all with heat shrink again. So that effectively gives me 2 legs of the same length. And that covers the whole thing over, so I'm not going to get a short from where the resistors are soldered to each other. Okay, I'm happy with that. I'm doing this at the customer's request, so it's entirely down to him with whatever happens, but I think this will probably work now. Okay, and there we have it. So it's all protected by heat shrink, nothing can short to anything. It's nicely soldered in there. Is this one soldered? I think so. It's just the heat shrink isn't tight against the leg. We can soon find out. End of this one to end of that one. 30k. So power up, the LED should come onto red, and then they should go out. Okay, red. Give them a few seconds. Off. Okay. I have a ground clip on my scope. I've just used the other probe. It's easier for me. So have the thing flapping around here by my wrist is not a good idea. So we can have like this is channel 1. And we have a square wave on there. This is channel 2 that wasn't working previously. And it now has a square wave on it. Channel 3. Square wave, and channel 4. Square wave. So that appears to be working now. I have a 50% duty cycle on all 4 channels. So I'm going to put this back together in the subwoofer case and see if it works. Okay guys, so the subwoofer's on the floor. It's just too heavy to get on the bench really. I haven't put the screws in tight. I've just stuck it together in case I have to take it apart again. I really hope not. It probably make a thump when I switched it on. That's what was happening before, but we can see, so we can see the lights on here. So let's just power it up and see what it does. All the lights are on, fan is on, all the lights went out. It didn't go thump like it was doing before. That is a good sign. Let's start some music, and we'll just turn the mixer up a little bit. So all we're going to hear is the bass. Oh yes. That's rattling the windows. That's fixed, guys. That is definitely working. So that's been a real journey, that one. But I think it's also, as much as being a repair, as being an educational journey. I decided this time to learn a lot more about subwoofers and Class D amplifiers in particular. I know now the next time I'm faced with one, pretty much what I'm going to check straight away. And you know what, guys? I hope you do. I'll link all the videos together in sequence in the description of this one if you want to watch the whole story and learn all the way along as you do. Hope you enjoyed that. Please comments below, and I look forward to seeing you all soon on Learning Electronics Repair. Ciao for now, guys.